So where we left off last class, we were getting ready to start looking at what happens with free fall. So with free fall, we have our gravitational acceleration. So gravitational acceleration, G, you may remember from Physics 1 that G is 9.8 meters per second squared. But what happens if well, if we look at the feet per second squared, we go to 32. So we have a rock thrown upwards, and it has. Now we're going to let up be positive. Well, what does that mean? It's going to be our positive direction. We're going to use G equals 32 feet per second squared. We want to know what is the rock's velocity at location if it has been rising for just 0.8 seconds. So what are we going to do? Well, we're going to go back to our kinematic. We're going to use y because we're looking vertically. Y equals y naught. That's what we're using. Plus v naught t plus 1/2 at squared. So our y naught, I'm going to call that 0 location. Although I could just as easily call that 24 feet up the cliff. But right now I'm just going to call that 0. So my initial velocity is 48 feet per second. We are going for 0.8 seconds. And we're going to have 1/2. Now because that G is pulling down, that's going to be a negative 32. And that's a really, let's fix that. So that's going to be a per second squared. And then we'll have that 0.8, and that is going to be squared. Now if we throw all of that in our random number generator, that we are 28 feet up in the air. Question we are asked, because I just jumped straight into how far are we. Now the other question we're asked is what is its velocity? How fast is it going in direction at location A? Well, that's equal to v naught plus at. And if I do that, we're going to start with 48. And then I have 32. And of course, that is a negative. So don't forget your negative, gremlin. Times 0.8 seconds. So that's 22.4 feet. So it's going in a positive direction. It's still going up at 22.4 feet per second. Part B. What rate of acceleration? Okay, well, let's think about this for a second. Humor me, if you will. At the tippy top of the path, the velocity that the rock is experiencing is 0. The tippy top of the path, that's what the velocity of B is. It's 0. What's the acceleration it's experiencing? Well, at that point, it's not like the acceleration has suddenly occurred. We are still undergoing the same gravitational acceleration of per second squared. It has not stopped. Gravity does not stop just because you're at the top of the path. So we want to know rate of acceleration. Boom, got that. How much time has elapsed to get to the top? Well, we could use velocity, v equals naught plus at. At the top of the path, your velocity is 0. Initially, your velocity is 48. You are having an acceleration of negative 32 feet per second squared, and you have time. So if you do some little mumbo jumbo, you are going to get that time is about 1.5 seconds. I want to know how far, how high up are we? Well, in this case, we're not using x, we're going to be using y, so let me go back here. We're doing vertical, so I'm going to stick with y. Y equals y naught, well, because I like y, plus v naught t plus 1/2 at squared. We started at 0, we called that 0. We had 48 feet per second initially, that was 1.5 seconds, plus 1/2 times a negative 32 times 1.5 squared. And yes, that should have a square. It's kind of going off the side of the page there. If we throw that in our random number generator, we're going to get 36 meters. 36 meters. So here we were at 28, here we are at 36. You notice that gap is not equidistant. Now, let's scroll down here. We need to know the velocity at location C. Now I want to point something out. What goes up must come down. So at this point, right here, we are 28 feet up. So if our velocity at point A was 22.4, and I lost a unit there, feet per second, going up at C by symmetry, our velocity is going down. So this would be by symmetry. We are looking at negative 22.4 per second. Now, how much time has elapsed? Well, we can in some cases invoke symmetry as well. We could also calculate it. So we know we are, if we look at our y equals y naught v naught t plus 1/2 a t squared, we are at 28 feet in the air. We started at 0. Our initial velocity was 48 times t plus 1/2 negative 32 times t squared. We can use our good old friend, the quadratic formula, and we would get 2 times. We would get this first one up here at 0.8, and we're going to get the next one is 2.2 seconds. Okay, well, what about at D? What do we know? Well, at D, we are back at that point that we are calling 0. And I know initially my velocity was going up at 48 feet per second. At D, by symmetry, my velocity is going to be going down at 48 feet per second. Now, another fun fact we should know, by symmetry, it took us 1.5 seconds to go from where we started all the way to the tippy top. It takes us 1.5 seconds to come back exactly to where we started. So if we look at problem D down here, D is going to be negative 48 per second. That is by symmetry. How much time has elapsed? 2 times the time to the top, again by symmetry, which means it's going to be 3 seconds. And we can do this with other calculations, but it's important to recognize the symmetry piece. So, the rock falls down the cliff and it lands at E. We want to know what is the rock's velocity at E and how much time has elapsed since the initial throw. So here's what I know. If I look at y equals y naught plus v naught t plus 1/2 a t squared, I've got negative 24 equals 0 plus 48 t plus 1/2 times negative 32 times t squared. If I do that, I'm going to get a number bigger than 3. I'm going to get 3.4 seconds. If I want to find my velocity is going to equal 48 plus that negative 32 feet per second squared times 3.4 seconds. So if I do that, I'm going to get that my velocity is negative 60.8 feet per second. Okay, so here we have a graph. And we have this little guy here, and we want to say that using the letters on the plot above, you want to indicate the time intervals during which the pedestrian is slowing down, speeding up, or just simply maintaining a constant walking speed. Now, here's something that you guys may or may not remember, which is that this is a simulation. This is the PhET's moving man. So I'm going to challenge you guys to go ahead and go to the PhET simulations and moving man, and to give yourself a few minutes to play with this and see what happens when he moves to the left, what happens if he moves to the right, and see if you can create this graph on your simulation. And using that, go ahead and answer those questions. We're going to come back to this next class and we're going to talk about our answers to this. Okay, so I want you guys to take a few minutes, do the PhET simulation, play with it a little bit, and see if you can create this graph.